Good afternoon, everybody. My name is Mike Heimlich. I'm a professor at Macquarie University. I'm going to talk today about a project that we did in conjunction with AWR, who I'd like to acknowledge and thank for having us here today. I'm going to talk about designing an ETSI compliant E-band set of circuits for millimeter wave telecommunications. The goal of these circuits would be applicable to a very high data rate point-to-point radio system in the 71 to 76 and 81 to 86 gigahertz bandwidths for very high data rate point-to-point. All right, first of all, just to put this in context, this project is part of a much larger research program, and I'll discuss in a moment the motivation for the research program, but it was funded jointly by the Australian Research Council, MACOM Technologies, and by WIN Semiconductor and Macquarie University, sort of as a consortium, if you will, of interested parties in coming together and solving a bigger problem. So I had the opportunity to lead this group in the research that we were doing, so I'd just like to acknowledge all the partners on the research here, because the majority of the work that I'm about to talk about, I'm just the program manager, so to speak, and I get to talk about it, but I didn't really do a lot of the actual detail work. Okay, the agenda for my talk is to start with a bit of motivation. We'll talk about the challenges on this project, which was pretty much new everything. We're also going to talk about the results for 3 chips in particular, a doubler, a quadrupler, and a power amplifier, and then some late results that we got very close to the submission for these slides, which put the results in some bit of context. And then in conclusion, we'll talk about the process overall. And that's really the focus of this talk, is the process that we went through to design this. The results of the actual chips were published in the 2012 Compound Semiconductor IC Conference. This talk is going to focus mainly on the process by which we were able to achieve that performance. Okay, so the motivation for the project in general is that if you talk to circuit designers like the folks at MACOM that we were working with, they'll tell you that historically when they get a PCM FET from a foundry provider such as WIN Semiconductor, they'll do some characterization on that FET, whether it's linear, nonlinear noise, load pull, what have you. When they compare that to the nonlinear performance of circuits that are near that PCM FET, they don't quite get the degree of correlation that they expect. And that's a little disconcerting for a number of reasons, but most importantly, they like to have a lot more certainty in their designs. So the real motivation of this project was, can we do things that are going to give more certainty? And one of the things that we're looking at is the inclusion of very small circuits in the PCM that can do a better job of correlating the PCM data, whatever that is, in this case it may be a circuit, to the performance that they find in the nonlinear circuits or highly nonlinear circuits that are on that wafer. So we term this a circuit control monitor rather than just a process control monitor, because we want to have that tie not just to the process but also to the circuitry. So the circuits that I'm going to discuss, the designing for the doubler, the quadrupler, and the power amplifier, were the validation circuits for this research project. And the research project in itself, the development of the circuit control monitor, is a bit of ongoing research, but we decided to report the results of the validation circuits because they were quite astounding in our opinion. Okay, so the challenges of this project were pretty substantial in my mind. I've done some MMIC design, but I've always done MMIC design using a process that I'm familiar with. If it's the first time I used a process, we'd play in that process, maybe design some circuits for fun or to just explore some ideas, but we would never try to design something that was targeted for a specific product, let's say, or a solution space right out of the box. We want to get a feel for that process the first time we design in it, the first time we get exposed to it. Similarly, when you're exposed to a new application, you want to do an engineering mask and get a feel for, well, can I meet those specs? How challenging is it going to be to put together things like linearity and power consumption, power out and power added efficiency? So typically before you ever really go in and try to accomplish the actual specifications for the system, you want to do it with a well-known process that you've used before, and you want to do it with a application space that you're somewhat familiar with. Well, in this project, we were unfamiliar with both of these. We decided to go after E-band because it was new and exciting, and we thought, well, we have this great new process that we can play with from Wind, their PP10 process, 0.1 micron P hemp power process, and we'll go after the ETSI spec because it's kind of new and exciting. So we'd never used this process. It was just being released by Wind Semiconductor. We'd never gone after this application space. We thought it would be a nice place to go and explore these ideas while we were developing the notion of the CCM. So we had a design team with an unfamiliar process and an unfamiliar set of specifications, but we did it, again, just to validate the CCM. Okay, so what did we start with? What was our initial approach? Well, at Macquarie University and in conjunction with MACOM and previously Mimics, we have a sort of a rich history of doing device modeling going back to the late 80s and early 90s. And we knew we couldn't do, let's say, all the modeling we would want because we had some pre-production PCMs, but what we decided to do was use a technique that's been very successful with other processes where we take a PCM FET of very well-known configuration geometrically, we extract a model for that and then separate out in the model the metallization from the actual semiconductor. So we get an intrinsic semiconductor model per unit gate length that's totally independent of the metallization. And in previous papers, I'm referencing one of them here, we've been able to demonstrate that the extracted linear model scales ideally down to 0. So in other words, the theory that we get presented as undergraduates when we do a JFET model, for example, says that if you scale the length and width of that device down to 0, your GM should go linearly down to 0, and your CGS should go linearly down to 0, and your input impedance should linearly go down to 0. This methodology allows us to do that for the intrinsic semiconductor. What we then do is we're able to define any device we want by taking the metallization and doing an EM analysis of that, and given the periphery of the FET that the EM analysis implies, we're able to recombine that with the semiconductor data and get a scaled model. And in previous publications, we've been able to demonstrate that this reproduces the S parameters for a very wide array of devices, no pun intended, up to 2x12 devices where we've scaled the actual gate finger length by as much as a factor of 4 or as little as a factor of a third. So we did that here with the new PP10 process. We did that for the linear model, we did that for the nonlinear model, and we also did thermal modeling as well, which I guess one of the people on the project who's sitting here, Brian, presented in a paper earlier in the IMS sessions yesterday. So we're able to scale these models and then reintegrate them together to get precisely the device that we want for the application that we need. So that was the first step in our design flow, if you will, to get a set of devices that we had confidence in, or at least confidence to the degree that the preliminary PCMs we had would allow. The second thing was the design flow. And again, the first part of the design flow is to get the device modeling done. We then implemented a design flow methodology which is somewhat like an onion. We peeled back the layers incrementally, but we did it in a somewhat unique way because of the challenges of 80 gigahertz, which I pointed out earlier with the slide that showed how little phase error you can really tolerate even at the mimic level. So in the initial design phase, we just tried to hit the linear nonlinear parameters such as they were at the schematic level and didn't worry too much about line lengths in the first go-round, knowing that we were going to lay things out pretty tight to begin with. What we then did is implemented each sub-block separately. So where circuits had matching networks on the input or interstage networks, we designed those separately, but EM'd them within the context of the layout, but just for that sub-block without any interaction with any adjacent blocks. Then we put those together and made sure that we, again, were able to achieve our linear and nonlinear performance. In the third pass through the design flow, we did the very same thing again, except look at adjacent neighbor interactions, where we could see what the interaction was between the metallization that we had designed for our custom FETs, if you will, with that interstage matching interconnect, and get those sub-blocks to work together for the linear and nonlinear specifications as they were given to us. And then finally, we went through a full-up final verification at the chip level. A key part of this whole thing was the AWR extract flow, which allowed us to do this in context in the layout, in the AWR layout system, and it was tied directly again to the simulation, so there was no piecing together of S parameter files. And because of our methodology of incrementally doing this, we're able to clearly identify when we had issues and where they were. So in the first pass through the EM extraction, we knew that any of the issues were within the sub-blocks themselves. In the second pass, we knew that any of the problems were with the interactions block to block. And in the final iteration, we knew that the issues were going to be between the larger blocks across the whole chip. So it was able for us, or it provided a methodology for us to, I'll say easily, although it's never easy at 80 gigahertz, easily identify where the issues were so we could go focus the engineering effort where we had to on the interconnects to get the performance that we wanted. So we had them fabbed, we taped them out, and this is the results that we got back for the E-band, Q to E-band doubler, which had greater than 15 dBm Pmax across the band. I'm showing here the results for 4 volts VDS. We actually can go up as high as 6 volts VDS. What you'll notice is that there's some pretty good agreement within a couple dB, which is pretty impressive for the first time you've ever designed in a process and the first time you've ever designed to a spec and the first time you've designed something this broadband at this frequency. There's pretty good agreement for the saturated power as well as the PAE, but maybe it's not quite as good as you would want, but for first pass through the design process, it's not such a bad thing. I'm actually setting myself up for a closer here that I think you're going to enjoy. The K to E band quadrupler probably looks a little bit better in terms of its performance and agreement between simulated, which is the dotted line, and solid, which is the measured. Again, if you want more details on the actual performance, refer to the compound semiconductor IC paper from 2012 that we published. Here's the S parameter data for the E-band PA, 23 dBm PSAT across the whole band at 4 volts. We got up closer to about half a watt with 6 volt VDS. Okay, when we got the chips back, we were a little disappointed with the accuracy. And maybe that's not fair to the process and to the guys at Win Semiconductor. Maybe it's not fair to the guys who are designing the chips. Maybe it's not fair to the people who are doing the modeling. But we were searching for reasons why we missed the power added efficiency in some cases by close to a factor of 2. And I need to remind you that small changes in PSAT are going to manifest themselves as very large changes in PAE because PSAT is a logarithmic measurement and PAE is a linear measurement. But we were sort of disappointed and we went back and tried to look at some of the data that we had separately. Again, look at that PCM data versus our nonlinear performance to see what we had. And on the PCM FETs, compared to what we had for the original model and what we had for the model on this wafer, we noticed that there was a significant discrepancy. So we went back and actually looked at the foundry data that we got, and it turned out that the wafer was right at the edge of the window for wafer thickness. So what we did is we ran the entire design through Analyst, the 3D FEM solver that I think John might have talked about in the previous talk, and we found out that the difference between the nominal wafer thickness that we had designed to and the wafer thickness of our actual wafer that was delivered was enough to account for nearly all the difference that we saw in our nonlinear characteristics as well as our linear characteristics. So here I'm showing the shift, for example, in the S parameters of my power amplifier simply by changing the wafer thickness itself from a nominal thickness of 50 microns to a thickness of 52 microns. And you can see how significantly the gain shifts because of that difference in the wafer thickness. So that difference all by itself can account for most of the difference that we saw between measured and simulated in our designs for this one example. So I guess in conclusion, I just want to say that you can design on the leading edge of technology, whether it's brand new manufacturing technology or brand new specifications. We had a set of very aggressive requirements in terms of the ETSI E-band spec. We used a brand new MMIC manufacturing process for something that we had never designed before, and we essentially got first pass success. I would say maybe we got a little unlucky in this case because the wafer thickness was sort of at the edge of the window, but had the wafer thickness been a little bit more down the middle, we would have been right on the money in a process that we'd never designed in and some specs that we had never seen before. So I think in summary, it all comes down to good design flow or good process, engineering process in general. If you do your homework in terms of device modeling, if you sweat the details in terms of the design flow, and quite frankly, if you have a tool set that can support sweating the process in that design flow, you can get things done in a reasonable amount of time with a very high degree of accuracy and assurance that what you simulate is what you're going to get. Thanks very much.